A gecko can sprint vertically up a perfectly smooth pane of glass at 3 feet per second, detaching and reattaching its feet entirely without hesitation. This presents an immediate mechanical paradox. Achieving that level of structural holding power against gravity usually requires permanent bonds, yet the animal can release its grip in roughly 15 milliseconds. Traditional high-strength adhesives rely on chemical bonds or ligway capillary action. While those methods create strong anchors, they are inherently slow to cure, difficult to reverse, and leave chemical residue behind. The gecko bypasses chemistry entirely. Its adhesion is a purely mechanical application of quantum electrodynamics. By reverse engineering this biological anomaly, mechanical engineers gain the blueprint for a high-strength, instantly reversible adhesive that relies strictly on physical geometry. To understand how this system operates, we have to scale down past the macroscopic mechanics of the animal and examine the physical forces governing atomic interaction. This diagram illustrates the Lennard-Jones potential, the mathematical model for van der Waals forces. These are intermolecular attractions that occur naturally between atoms. Next to it is the massive downward vector of gravity, the constant force the animal must overcome. On their own, van der Waals forces are incredibly weak. At a macroscopic scale, their attractive pull is entirely negligible compared to the massive drag of gravity. We are going to reverse engineer this mechanism from the bottom up, tracing how the sub-micron physical geometry of the foot integrates with specific kinematic motions to bridge that gap. The system does not alter the laws of physics. Instead, it utilizes a highly specific structural hierarchy to mathematically scale weak atomic interactions into macroscopic strength. Van der Waals forces manifest as transient electron cloud fluctuations. Shifting electrons create temporary dipole connections, weakly attracting two surfaces together. Because these interactions drop off dramatically over fractions of a nanometer, a single point of atomic contact provides practically zero usable adhesion. To solve this, the biological system uses a microscopic base structural unit known as a spatula. When you isolate one single spatula pressing against a glass substrate, the resulting force vector is minuscule. That solitary spatula cannot support meaningful mass. To hold up an entire organism, that baseline force requires an immense exponential multiplier. The fundamental engineering bottleneck for utilizing intermolecular forces is pure geometry. You must maximize surface area contact at the microscopic level. A single spatula duplicates exponentially into a dense array of millions on one stalk, the keratinous setae. Its flexible keratin stalk forces these rigid terminal tips to contour deeply into uneven microtopography. Summing these millions of contacts generates an exponentially larger macroscopic adhesive force. This hierarchical architecture acts as the necessary bridge, giving molecular-level physical interactions the surface area they need to anchor against a macroscopically rough world. It is a common misconception that the foot itself is intrinsically sticky. At rest, it exerts almost no attractive force. The system relies on a mechanism known as directional friction. The adhesive properties only activate when subjected to a highly specific mechanical load. This schematic demonstrates the necessary load, shear force. The setae array must be pulled downward, applying tension parallel to the surface. This directional shear physically tugs the branched spatulae, dragging them flat against the substrate. Laying flat geometrically guarantees maximum van der Waals contact area. You can clearly see how the macroscopic physical tension applied by the limb forces the microscopic, hair-like structures to flatten and engage. The system functions as a purely mechanical lock. High-strength adhesion is generated only when the organism inputs precise, directed kinematic vectors. While the shear force lock generates immense holding power, the organism must break that lock in milliseconds to maintain its running speed. The solution is mechanical toe peeling. This schematic outlines the toe dynamically increasing its upward angle relative to the surface. Crossing a specific detachment angle threshold instantly neutralizes parallel shear force. Without that parallel tension, peeling sequentially breaks the microscopic van der Waals bonds. By utilizing peeling geometry over brute force chemical adhesion, the system reduces detachment energy cost to a mere fraction of a direct perpendicular pull. This split screen unites the entire mechanical life cycle of a single footstep. On the left, the macroscopic toe applies shear load and peels upward. On the right, the microscopic setae perfectly mirror that input. Notice the exact synchronization. The moment the toe drags downward, millions of microscopic spatula flatten out to maximize surface area contact. Then, as the toe alters its upward angle, intermolecular bonds sequentially snap, cascading cleanly down the array. This entire cycle of locking and releasing happens in a fraction of a second, and it leaves absolutely zero chemical residue behind. The paradox of immense hold and rapid release is solved entirely by a geometry-dependent kinematic architecture designed specifically to scale the weakest quantum forces into immense mechanical strength. Biologists have mapped the mechanism, and material scientists are actively applying it. The overarching hierarchical structure of the gecko provides a direct blueprint for engineering artificial, dry, entirely reversible adhesives. Mechanical engineers are already replicating the geometry of keratinous setae, fabricating artificial, dense bristle matrices for use on the end effectors of industrial robotics. This has massive implications for automated manufacturing. Robotics equipped with these matrices can apply immense shear grip to move fragile components, like silicon wafers or glass panels, and then instantly detach without introducing any chemical contaminants to the assembly line. The future of extreme, reversible fastening does not rely on synthesizing stronger chemical glues. It relies on engineering smarter physical structures that can harness the fundamental intermolecular forces of the universe.